You are familiar with the first, second, and third derivatives. But can there be a derivative of order 1/2 or an integral of order 0.7? Fractional calculus is the branch of mathematics that extends differentiation and integration to any order, real or even complex. This video is based on the lecture by Weil Amends from It All Began in 1695. The mathematician L'Hopital wrote to Leibniz asking, what if the order of the derivative were 1/2? Leibniz replied that this would lead to a paradox, from which one day useful consequences would be drawn. That prediction came true. In 1730, Euler found the key. The nth derivative of x to the m equals m times m minus 1, and so on, times x to the m minus n. Euler rewrote this product using the gamma function, an extension of the factorial to non-integer values. This makes the formula meaningful for any order, and taking m equal to 1 and n equal to 1/2. Euler obtained the half derivative of x equals 2 root a. To generalize systematically, we start from integration. Taking n successive integrals of a function by Cauchy's formula can be collapsed into a single convolution. Integral 1 over factorial n minus 1 times the integral of t minus tau, all to the power n minus 1 times f of tau. This is the most important stepping. The key idea: replace factorial n minus 1 with the gamma function of n. Now, the order n need not be an integer. It can be any positive real number alpha. We obtain the Riemann-Liouville fractional integral of order alpha, 1 over gamma alpha times the integral from 0 to t of t minus tau to the alpha minus 1 times f of tau. According to Gorenflo and Mainardi, this is the foundational definition of the whole theory. Now that we have the integral, how do we get a derivative for alpha between m minus 1 and m? We first apply the fractional integral of order m minus alpha, then take the ordinary derivative of order m. A surprise: the fractional derivative of a constant is not necessarily 0. The Riemann-Liouville derivative of 1 equals t to the minus alpha over gamma. 1 minus Caputo proposed a different route. Differentiate first, then integrate fractionally. The difference is small but crucial. With the Caputo derivative, the derivative of a constant is always 0, and the initial conditions are stated through the function's own value and its integer derivatives. That is why Caputo is widely used in physics and engineering. So far, we differentiated in time. What about space? Riesz-Feller defined the fractional derivative in space through the Fourier transform. In the frequency domain, the operator is simply multiplication by the absolute value of k to the alpha, with a phase shift given by the parameter theta. Theta measures the skewness of the operator. A third, very intuitive viewpoint comes from Grunwal and Letnikov. Recall that an ordinary derivative is the limit of a difference, quotient over a step h run wild. And Letnikov generalized this finite difference to order alpha, using generalized binomial coefficients. Then let the step h go to 0. This definition is especially useful for computation. In ordinary calculus, the exponential function solves the relaxation equation. In fractional calculus, that role belongs to the Mittag-Leffler function, a series like the exponential, but with gamma alpha times j plus 1 in the denominator. Solutions of fractional relaxation and oscillation equations are expressed compactly through this function. When alpha equals, this is where fractional calculus shines in practice. The classical diffusion equation describes ordinary random motion, with variance growing linearly in time. Replacing the derivative with a fractional order in time or in space gives anomalous diffusion, faster or slower than normal. According to Mainardi, Luchko, and Pagini, the green function of this equation is a stable Levy distribution. What is the geometric meaning of a fractional integral? Podlubny gave a beautiful picture of a fence and its shadow. The ordinary integral is the area under the curve seen head-on. The fractional integral is the area of the shadow of that fence. As the fence is bent and deformed over time, the order alpha controls how much the shadow is deformed. In summary, from a curious question in 1695, Fractional calculus has become a powerful tool for physics.